Welcome to the series of exponential and logarithmic functions. In this series, we will explore the exponential and logarithmic functions through worked examples. As you probably know, exponential functions have important life applications, particularly in the phenomena of growth or decay. For example, it can be used to model the value of an investment or sales of a company, which increase by a constant rate in each period, economic growth, or even the spread of an epidemic. In general, exponential functions solve the simplest growth models, such as bacterial growth and the doubling time or half-life of a particle, indicating the rate of growth or decay. Like many types of functions, the exponential function has its inverse. This inverse is called logarithmic function. It can be used to solve and explore the properties of exponential functions. Both exponential and logarithmic functions are extremely valuable in calculus, where they are used to calculate the slope of certain functions and the area bounded by certain curves. In the first session of this series, we are going to introduce the exponential and logarithmic laws along with the graphs of these functions. Applications-wise, we will demonstrate how to apply the exponential and logarithmic laws to solve basic and advanced questions.
Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding, so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything.
Welcome to the series of exponential and logarithmic functions, and this is the first session of the series. In this session, we are going to briefly introduce the index logarithmic laws and their functional graphs, as well as how to apply them to solve basic and advanced equations. Let's recall that a number a, which is multiplied by self y times, can be represented in index notation as shown on the display. Here a is called base, y is called index or exponent or logarithm. X is called base numeral or base argument in some cases, while in logarithmic form, y is equal to logarithm base a of x. Both equations represent the same relation but in different form. In fact, logarithmic function is an inverse function of exponential function, and vice versa. It is important to note that the base a is a real number but must be greater than 0 and not equal to 1. Now, let's briefly look at the index law as shown on the screen. When terms with the same base are multiplied, the indexes are added. When terms with the same base are divided, the indices are subtracted. To raise an initial expression to a power, multiply the indices. As a fractional index like a to the m over n, it can be expressed as nth root of a raised to the mth, or the nth root of a, or in parentheses raised to the mth. Negative index can be expressed as 1 over the base numeral. Any term with an index of 0 is equal to 1. As for the logarithmic law, as it can be seen, the logarithm of a product is the sum of their logarithms. The logarithm of a quotient is the difference of their logarithms. The logarithm base a of m to the nth equals n multiplies logarithm base a of m. The logarithm base a of 1 over n equals negative logarithm base a of n. The logarithm base a of a equals 1 and logarithm base a of 1 equals 0. The diagram on the left shows a set of exponential curves with different base. In general, there are two basic shapes for exponential graphs, increasing or decreasing. As it can be seen on the screen, when the base a is greater than 1, the exponential curve is an increasing curve. When the base a is between 0 and 1, the exponential curve is a decreasing curve. As for exponential equation, one common method is when both sides of the equation are powers with the same base, and then to equate the indices. The diagram in the middle shows a set of logarithmic curves with different base. Like exponential curve, there are two basic shapes for logarithmic curve, increasing or decreasing curve. When the base a is greater than 1, the logarithmic curve is an increasing curve. When the base a is between 0 and 1, the logarithmic curve is a decreasing curve. As explained earlier, exponential equation a to the x equals b is equivalent to x equals logarithm base a of b. Logarithms can be used to solve exponential equations and inequalities. The graph on the right shows two sets of exponential and logarithmic curves on the same base. It can be seen that the curve of y equals logarithm base 2 of x is the reflection in y equals x of the curve y equals 2 raised to the x, while the curve of y equals logarithm base 1 over 2 of x is the reflection in y equals x of the curve y equals 1 over 2 raised to the x. Since an exponential function is an inverse function of its corresponding logarithmic function and vice versa, the domain of an exponential function is the range of its corresponding logarithmic function. The range of an exponential function is the domain of its corresponding logarithmic function. The first worked example is to evaluate 5 initial expressions. As for the first question, we rewrite the base in terms of its prime factor, which is 5. So 125 raised to the 4 over 3 can be expressed as 5 cubed raised to the 4 over 3, which equals 5 to the 4th, which equals 625. We use the same approach of rewriting their bases in terms of their prime factors for the rest of the questions, and then proceed with the exponential laws to obtain the corresponding results as shown on the screen here. As for the second expression, the base 16 over 81 can be rewritten to 3 over 2 raised to the 4th. The base 8 over 27 in the third question can be rewritten to 2/3 cubed. The base in the question 4 can be transformed to 4 over 11 squared, and the base of the last question can be expressed as 5 over 6 cubed. The second example is to evaluate 2 exponential expressions. As for question 1, we rewrite the base number in terms of its prime factors, such as the number 6 is written to 3 times 2, and the number 4 is written to 2 squared. Then, based on the same base, 2 or 3, we proceed the simplification with index laws, and then obtain the simplified result of 3 over 2, or in parentheses to the 3/4. As for question 2, we express each term in both parentheses with the same base and interchange the numerator and denominator by changing the signs of the indices. Then we multiply the indices to the power and then proceed the simplification with the appropriate index laws, and then obtain the result of 1. Example 3 has 3 initial expressions to simplify. For question 1, after rewriting the base number in terms of its prime factors, it has 2 different bases of 2 and 3. Based on the same base, we may proceed the simplification with appropriate index laws. The final simplified form is 3 to the 9n minus 3 multiplies 2 to the 5n minus 6. Question 2 is to simplify a fractional initial expression with the base 3. After taking the common factors on both numerator and denominator, the result of 3 is obtained. We take the same approach for the last question by moving out the common factors on both numerator and denominator. After cancelling the common factor 5 to the nth, we obtain the result of negative 2 over 3. Example 4 has 2 initial expressions to simplify. For the first question, we rewrite the base 25, 125 to 5 squared and 5 cubed respectively. Then we proceed the simplification with the index quotient rule and obtain the simplified form 5 to the 5 twelfths minus 5 to the 5 fourths. As for question 2, we transfer the expression to the fractional index form. Based on the same base a, the simplification can be proceeded with the index quotient rule, and then we obtain the result of a to the 5 over 6. Example 5 is to solve an initial equation. After initial observation, it is found that all the bases can be transformed to base 2. So the equation becomes 2 to the 3x multiplies 2 to the 4 times x plus 1 in parentheses equals 2 to the 5th. Since the base on both sides is same, the indices of both sides must be same. After solving the linear equation, x equals 1 over 7. Example 6 is to find the domain and range of 3 exponential functions. As for the first question, according to the function rule 1 over square root of 1 minus 3 to the x, here 1 minus 3 to the x must be greater than 0. After solving the inequality, the domain of x is obtained, which is less than 0. Since 3 to the x is greater than 0, then when x approaches to 0, y approaches to infinite. When x approaches to negative infinite, y approaches 1. Therefore, the range of this function is greater than 1. In summary, the domain of the function is less than 1, while the range of the function is greater than 1. As for question 2, since the function rule is y equals 4 to the x minus x squared, the implied domain of this function is the whole real number. Since the initial expression can be transformed to the quadratic turning point form, which is negative open bracket x minus 1 over 2 close bracket squared plus 1 over 4. So the value range of the quadratic index is from negative infinite to 1 over 4. Hence, in summary, the domain of the function is R, the real number, while the range of the function is from 0 to square root 2, including the point of square root 2. Here we continue work on question 3 of example 6. Since the rule of the function is y equals 1/3 raised to the square root x, the domain of this function x is obviously greater than or equal to 0. due to the base is 1/3, which is less than 1. The function is a strictly decreasing function. Therefore, the range of the function is between 0 and 1, including the point of 1. In summary, the domain of the function is greater than 0, while the range of this function is greater than 0 and less than or equal to 1. Example 7 is to find the function which is symmetry to the curve of y equals e to the 2x minus 2 times e to the x plus 1 about the line y equals x. Since the function we are going to find is symmetry about the line of y equals x, it is actually the inverse function of the given exponential function. To find its inverse, we interchange x and y based on the given function. Since e to the 2y minus e to the y plus 1 is a complete square of e to the y minus 1, or in parentheses squared, so e to the y minus 1 equals square root x. Hence, its inverse is y equals natural logarithm of 1 plus square root x, where x is greater than or equal to 0. Y is also greater than or equal to 0. Example 8 is to solve two exponential equations. The first one is 5 to the 2x multiplies 25 to the result of 2x minus 1, which equals 625. Since 25 can be expressed as 2 squared and 625 can be expressed as 5 to the 4th, we rewrite all the bases to 5, and the equation becomes 5 to the 2x multiplies 5 to the result of 2 times open bracket 2x minus 1 close brackets, which equals 5 to the 4th. Since both sides of the equation have the same base, 5, we equate their indices and then obtain the result of x equals 3 over 2. As for question 2, since this equation can be reduced to quadratic form, we may apply the quadratic technique to find values of 7 to the x. After factorizing the equation, we have the values of 7 to the x that are 1 over 7 and 1 respectively. Hence, we obtain the values of x that are -1 and 0. Alternatively, we may transform them to the logarithmic expression to obtain the results.
If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.